Thank you for joining me on Project Tech Statistics YouTube channel. Today we're going to talk about normality tests in SPSS using a nominal data. For a parametric statistics to actually work optimally, you need to ensure that your data set is normally distributed. And this is a very important assumption for many statistical tests. For example, we have the t-test, the ANOVA test, the regression, and the Pearson correlation. So these are parametric tests that require that your data be normally distributed before they can work optimally. So conducting a normality test in SPSS is used to check if the data set follow a normal distribution. Now, first of all, what is normality? The normality referred to as how closely the distribution of your data resemble a bell-shaped curve. For data to be normally distributed, they have to have the form of a bell shape or a Gaussian distribution. Now, this is an example of a data that is normally distributed and the one that is not normally distributed. As you can see, the one with this yellow one here, you have that this is a normally distributed data with bell shape. You can see the bell shape, and when you draw the line here, you see that the thing actually fits into this bell shape line accurately. So this is an example of a histogram output of a normally distributed data having a bell shape. And look at this one here to my right. You see that this one is not normally distributed. As you can see that the data, most of them did not follow the bell shape, and you can say that this particular distribution here is not normally distributed. So as you do your analysis in SPSS, you get your histogram output. You have to look at the output and see that the output follow the histogram follow a bell shape, and if it does not follow the bell shape, you know that your data is not normally distributed. This is a first call of virtually looking at your data distribution to know if it is actually uh, normally distributed or not before you proceed to do other test-based analysis. Now, meeting normality test assumption. There are a lot of things that you have to consider to ensure that your data distribution meet the normality assumption. And there are a whole lot of things you can consider, and some people are really confused about how to see if their data is normally distributed. The first one I have in my list here is using your test-based analysis in SPSS, which is the Shapiro-Wilk test. You can as well use the Kolmogorov-Smirnov test, which is also equivalent to Shapiro-Wilk test. We're going to see how to do that in SPSS as we progress. Now, if you conduct that test and you see that your p-value is greater than 0.05, it means that that data is normally distributed. Anytime your p-value is greater than 0.05, that means you are going to accept the null hypothesis that the data distribution is normal. Another factor you have to check is your the mean. If the mean is equal to the median, then that data is normally distributed. So in your descriptive statistics, if the mean is equal to the median, you can say that that data is normally distributed. Or if there is any slight, if there is slight difference between them, you can also say that they are approximately distributed. Then another thing is, I've talked about this earlier on. The histogram visual show that the data is happening. So you need to check the histogram output to see if it follows the normal distribution, the bell-shaped curve. If it follows that bell-shaped curve, so you need to visually look at your histogram to see that your data is normally distributed. Another factor you have to check is your skewness. For a normal distribution, skewness is equals to 0. So the skewness of a normal distribution is 0. So you have to check if your skewness is 0. And sometimes a rule of thumb for judging normality, you can say that the skewness, if your skewness is slightly below 0 and slightly above 0, you can also say that your distribution mirrors a normal distribution. So if your skewness is between minus 0.1 and plus 0.1, you know that D is very, very close to 0. So you can actually say that that distribution is approximately normal. Now, for kurtosis, we have for a normal distribution, the kurtosis is equals to 3. But there is something that we call the SS kurtosis. SPSS or many other softwares report what we call SS kurtosis by using 0 as the normal reference point instead of 3. But actually, in real sense, the real kurtosis the real kurtosis for a normal distribution is 3, but SPSS don't report 3. SPSS uses what we call the SS kurtosis by using 0 as the normal reference point instead of 3. What it means that SPSS subtracts 3 from the normal kurtosis and now use 0 as the reference point in its output. And SPSS does this um, adjustment to make interpretation simpler. So most time when you see your kurtosis output, you have to know that 3 has been subtracted from that value you see in the SPSS output. 3 has been subtracted. So SPSS, whatever value SPSS um gives you in the kurtosis, just know that 3 has been subtracted from that value before it is being outputted in the SPSS output. So here you see that for kurtosis, if you the SPSS output, if the kurtosis is between minus 0.1 and minus 0.1 and plus 0.1, you can also say that that kurtosis is normally distributed. Normally distributed. So that is what happened here. SPSS uses 0, but the normal kurtosis of a normal distribution is actually 3. But SPSS subtract the 3 to make the interpretation a little more easier. Now, another way you can also know that a distribution is normally distributed is the Z value of the kurtosis and the skewness. The skewness and kurtosis Z value are in the range of minus 1.96 to plus 1.96. So this range here, you get it by dividing the skewness statistics by the standard error. So we're going to see that in SPSS output and how we can compute it. How we can compute. This one is very important for you to know because it's a good confirmation. And in doing that, make sure that you also add the 3, that 3 that has been subtracted from that kurtosis. You add it before you do your subtract and you do your division here. So I'm going to take us to SPSS. Okay, this is a categorical data. It's actually a nominal data involving two categories. So we're going to go to analyze, compare mean, descriptive, explore. In the explore, you are going to put your dependent variable here, which is the lifespan and the diet. So here we go to descriptive statistics. Then in the plot, you enable the histogram and also enable the normality plot with then all untransformed. So under the spread and the level with Levene test, you use the untransformed. So here you go and you click OK, and we allow the SPSS to. So this is the output here. First of all, I told you that you are uh, for you to confirm that your data is normally distributed, you go to your normality test. If the p-value is greater than under the Shapiro-Wilk, if the p-value is greater than 0.05, you you know that your data is normally distributed. But here we can see that our p-value here is less than 0.05, so we can clearly see that this data are not normally distributed. Both the restricted diet group and the ad libitum group are not normally distributed. So from here, you see that our p-value is less than 0.05. The Shapiro-Wilk p-value is less than 0.05. Let me go back. So I told you that your p-value, the p-value of your Shapiro-Wilk must be greater than 0.05 for your data to be normally distributed. But in this case, it is less than 0.05. So we can clearly see that the data is not normally distributed. Now, in handling the second one, if the mean is equal to the media, if the mean is equal to the media, we also say that this data is normally distributed. So let me go back here. The mean here is where is the mean? Okay, see the mean here. The mean here is 327 and the media is 231. So you can clearly see that the difference between the mean and the media is very, very large, and you can clearly see that this um, the restricted diet group does not have a normal distribution because the mean is very much different from the media. So if these two numbers were close to each other or equal to each other, you can say that the data distribution is normal. But in this case, it is not. If you go to the ad libitum group, you also see that the mean here is 153 while the media is 163. So there is a big difference between the both of them, which confirm the fact that this ad libitum group, the distribution is not normal. So that is for point number two. Let's go back to our other now here in the number three, if the histogram visual show that the data are approximately distributed. Okay, when you come here, you also see that the visuals here, you can see that the visuals here, they are not showing any form of normality here. Let me open let me click and show distribution. Show distribution curve normal. So as you see that this histogram here did not follow a normal distribution. you can clearly see that this one is not normally distributed and this one is not also normally distributed. So the histogram visual has shown that this data is also not normally distributed. Let me go back to the third one or the fourth one here. For a normal distribution, the skewness is equals to 0. Now here, let me go to the skewness. As you can see, the skewness here is not equals to 0. So the skewness is very high here. So if your skewness is according to here, you see that the rule of thumb here for judging normality is that the skewness is between minus 0.1 and plus 0.1. So you see that the skewness here is way above 0.1. So you can clearly see that the skewness here is not close to 0. And here, this one is also minus 0.6, which is a little bit far from 0.1, as you can see. So here now also show you that the skewness, that the two distributions are skewed, they are not normal. Now in the fifth one now, for the normal distribution, the kurtosis is 3. But I told you that for some softwares like SPSS report what we call the SS kurtosis, they use 0 as the normal reference point instead of 3. Yes, that's okay. So they use 0, and you can clearly see that kurtosis here falls between 0.1 minus 0.1 and the plus 0.1. So if you go back, you will see that your kurtosis here is minus 0.8, which is also very high, far away from 0. Here, this one we have 0.2, which is also higher than 0.1. So you can see that it is a bit far. And I told you that the normal kurtosis, SPSS report uses 0. What it means that for all the values of the kurtosis here, you are going to add 3 to it, because SPSS subtract 3 from the normal kurtosis and report SS kurtosis. So this value here now is known as SS kurtosis. What it means is that 3 has been subtracted from this figure. 3 has been subtracted from this figure. Now, for you to interpret your kurtosis very well, you need to add the 3 here. If you add the 3 here, you will see that this is going to be 3.205, and this is going to be 3.845 if you add your 3. And that will lead me to the next point, which is our number 6. The number 6 here said that the kurtosis, the skewness and kurtosis Z value are in the range of this and this. So how do we calculate it? We're going to calculate the Z value of your kurtosis. We're going to use kurtosis statistics divide by the standard error. Let me go back. I'm going to say, if you check this now, you're going to see that for my skewness, if I do 1.182 divided by 0.27, let me do that with my calculator. Let me bring calculator. Okay, so my skewness here, I'm going to say 1.182 divided by 0.272. So as you can see that this value here now, 4 points, is not in the range of what we got, which is 1.96. So this value is not in that range. This value now, 4.3, is not in the range of -1.96 and +1.96. So what it means is that the Z index of your skewness is out of the range. And what it means is that it's also confirming the fact that this distribution is not normally distributed. Now let me do the one of kurtosis. If to do the one for kurtosis, I'm going to, instead of using 0.205, I'm going to add 3 to it, because if you do it like this, you are going to get a wrong answer. For example, if I do 0.25 divide by, sorry, 0.2, sorry, let me do that again. 0.205 divide by 0.538. If you do this, you see you are going to have a number that is within that range, and is going to be contrary to what the other statistics have shown us. So in order to get the right calculation, you will add 3 to this thing, because SPSS normally remove 3, subtract 3, and then report SS statistics. So here we're going to do 3.205. That's what we're going to use. Divide by 0.5, 0.538. And when we do that, we're going to have a value that is away from the range, which is -1.96 and +1.96. So this value is also outside that range, which means that it indicates that the value is not normally distributed. So this is a very important point to note, that SPSS always subtract 3 from the normal kurtosis and report SS kurtosis. So the value that you see here, 3, has been minus or subtracted from it before it is being displayed. So anything you want to do on this data, you have to add 3 to it for you to get the right evaluation. So here we can clearly see that all our test has indicated that these values are not normally distributed, and all our point has shown exactly consistency that this data is not normally distributed. So as you can see, that's all our 6 points here meeting the normality test has been consistent, and we can clearly see that for any analysis you are doing, for you to test your normality test, you have to conduct all these tests, and most of the time, you will get, you know, a consistent result for you to really know that your data is normally or not normally distributed. And when you are conducting your normality tests, I always love to state my null hypothesis, that there is no difference between the observed data distribution and the normal distribution. That is the null hypothesis of a normality test. Or you can actually say that the data distribution is normally distributed. So if your p-value is significant, you reject. If it is not significant, you accept. So that is where this p-value comes on here. If your data is normally distributed, it is going to agree with the null hypothesis. That is, you accept the null hypothesis if your p-value is greater than 0.05. Okay, thank you very much for your time. Kindly subscribe to our channel, like and share.